All right, so you're all here for 535, right? All right, so this is in our graduate program, our first computer programming class. It's the prerequisite for 537, but as I see some faces out there, some of you guys took 537 first. So you're going to have to pretend like you haven't seen some of this stuff before, but I guess deal. Some of you sucked at 537, so it didn't matter. In any case, grades in this class. Syllabus is up on Angel. I have to unlock Angel. I'll do it at the during our break. But grade breakdown in this class. 80% of your grade, homework and reports. 20%, final exam. Final exam will be an in-class final during the second half of the last class. But any of the stuff we cover in the first half of the last class won't be on the final. Okay? So most of your grade is made up of the homework and the reports. So each week you're going to have a programming assignment. The first week's programming assignment is probably the easiest one, but after that it's going to be fairly hard problem solving for most of you. So you'll have a programming assignment that you complete in Java, which I assume you've never had any programming in here. So when as I start going through the slides today, it assumes you've never seen this stuff before. So we start at a fairly remedial level. So some of you might be bored with it, but hopefully it'll be challenging for most of you rather than starting you off on too difficult of a step. So every week you'll have a homework assignment. You'll also have a paper to write. It's typically a 2 to 3 page paper on some sort of related topic. So every one of these is worth the same amount. So a homework assignment and a report are worth the same amount. Each one's worth 100 points or whatever. Some things to keep in mind with the reports is, since at least for many of you, English isn't your first language, I don't want the paper to read like it's broken English. So I encourage you to take it to the writing center or something like that. Have somebody proofread it, because you lose points pretty quick that way. I'm not going to really knock you for too much grammar. I want you to try, but I'm not going to grade it like an English teacher. I'm grading it like a technology person. But one of the things you're going to have to accomplish as an IT professional is you're going to have to be able to verbally and textually communicate with people. So my job is to prepare you for working in businesses over here. So you need to be able to communicate clearly in English. So if you feel like you might have a problem with writing, just make sure you put it in front of somebody before you put it in front of me. All right? Have somebody proofread it. Take it to the writing center. They'll make it sound less like broken English. Make sense? Okay. So having said that, don't be offended if I say that your paper sounds like broken English. Again, the final exam, 20%. It'll be a written exam, mostly programming. That'll make more sense to some of you who've never had programming. Just out of curiosity, how many of you have never done anything with computer programming before? Should at least be a couple of you. Don't be embarrassed.
It's about Java. I've never done Java.
Programming is programming, but okay. But yeah, we're looking at Java in here. That just happens to be the language I use. We'll talk about why here in a few minutes. And I know the two in the back have had quite a bit of programming. Anybody else in here pretty strong in programming? Okay. So at least for the time period, you guys aren't allowed to answer questions. Well, I want you to try to answer questions if I want you to answer. Sometimes I throw a question out there that I purposely want you to answer wrong. That way it starts a discussion we can talk about. But if you want to cheat off somebody on homework, those two guys would be pretty solid in the back. This is much more of a necessary requirement for them. Okay, so questions on the grading in the class. It's a standard 90, 80, 70 grading scale. Top and bottom 2% are pluses and minuses. So nothing crazy there. In the past, I've done some stuff with extra credit. I probably won't do that anymore. And that's really your peers' fault. I end up getting a zillion emails about 30 different ways of calculating your grade and stuff like that at the end. So I'd rather just do it straight up, so don't suck. Okay, questions about grading for the class at all? All right, well, then let's dig in. And like I said, for some of you, you may have seen some of these things before. Oh, I'm already on the keynote. Oh, one last thing. I do record all the lectures, so you'll see this clock thing going on up here. We usually, for this class, since it's a 4-hour straight class, which I don't agree with, first of all, just as the nature of the beast, how our program works. This is a difficult subject, and I expect it to be difficult for many of you. Some of you have had this stuff before, predisposed to it, but this should be a difficult class for many of you. And frankly, getting it in 4-hour chunks is not the right way to get this material. It just is what it is. So in any case, I do record all the lectures. We usually go for about 2 hours, and then we take a break, then go for another hour and a half, something like that. You'll definitely be out by 10. Sometimes we try to get out by 9:30, 9:45, whatever. But I do record the lectures so you can go back online and review them and stuff like that. Because at some point during a 4-hour lecture, your mind goes to mush. So I get it. If you do need to get up and go take a break or something like that, just do it. I won't be offended. I don't like talking for 4 straight hours any more than you like sitting here for 4 straight hours. But because a lot of you are working professionals, this is the way you have to digest a master's degree, and it's just a necessary evil. Okay? So understand that I feel your pain. But specifically with computer programming, this is, I think, a very poor format to get it 4 hours at a clip, because it's really one of those things you got to go practice and then suck at, and then come back and work on it, then go practice, and compressing it into 8 weeks it's an uphill climb. So I apologize in advance, but is what it is. Okay. So let's talk about problem solving. And again, for those of you who had some of my other classes, you heard these exact slides before. So human beings are really, really, really good problem solvers. We're so good at problem solving that we forget how we solve problems. The example I always use is, so we all walked to class today, right? How many of you bumped into walls on your way to class? We all missed the walls, right? Okay, and I know a couple of you, that's a feat. Okay, so you missed the walls. How? How many of you thought about missing the walls as you were coming to class? Did you actually even think about the walls? They were just there, almost passive, right? How many of you were actually texting while you were walking the halls? You were screwing around on your phone, not even looking in front of you, and you still missed the walls. How did you do that?
Naturally.
Just don't think even about it.
Okay, well, so now think about it a little bit. So I'm asking you to at least process it a little bit.
Maybe I have an image of how will I move and just make it so that will go straight.
Okay, so somewhere you think you're subconsciously kind of looking at your surroundings, figuring out what the heck's going on around you, right?
Mm-hmm.
And if you think you're starting to head towards something bad, you adjust, right? It's a lot more complex than that, likely, because now, if you think about that, you break it down into all the little baby steps. You have to, what does it mean to adjust? Well, you have to start putting strength into some muscles and, contracting some muscles and things like that just to get your course to change. So many things had to happen as you came from the parking lot to class today for you to miss those walls. But every one of you did it. Some of you did it without looking, right? So the problem with the reason why computer programming, which is what we're going to talk about in here, the reason why that's so difficult is because human beings are really good problem solvers. We're so good at solving problems that we have forgotten how we solve many problems. We have a difficult time explaining to other people how we solved a problem. You did something very complex today by walking to class without hitting a wall. Yet, when you tried to explain it, you just said, I just did it. No big deal, right? And there was how did you walk? What if you had to explain to me how to walk? we've been doing it for years, right? I mean, we kind of sucked at it when we were babies. Fell over a bunch of times, everything seems so easy when you're on all fours, but now all of a sudden you gotta, so what is walking? If you had to give me a recipe for how to walk.
In my physics class in like 10th grade, my teacher asked all of us how humans control their gravity point when they are walking.
Okay.
But it's so difficult that none of us can explain because when we are moving, we are just trying to keep the gravity point not too extend from our body, but we have to make it in front of us. Otherwise, we cannot walk front.
Sure. So it's where your center of gravity is. So really walking is all about losing your balance and catching your balance, right? So, and it kind of, that you're talking about physics. Interesting fact is, did you know that you use more energy going downstairs than going upstairs? That doesn't seem right, but it's true. Because wouldn't you rather go downstairs than go upstairs? Climbing stairs sucks. But it's because when you drop down a step, you're having to catch all your body weight with gravity having an impact on it, and you have to stop it with your muscles. Doesn't feel as hard, but you're actually expending more energy going down. Weird. But in any case, walking is all about losing your balance and catching your balance. And then somehow continually throwing yourself forward or throwing yourself backwards if you're walking backwards to get somewhere. So even just the act of walking is complex. And that, what we just said there for walking is high level. Right? That's a high level explanation of walking. We're not even talking about how do we make certain muscles fire and stuff like that. When you were a baby, when you were a day old, you couldn't do anything. You just sat there and cried and pooped. That was all you did, right? Okay? You were still learning how to use your body parts. You couldn't move your arms and stuff like that. So these are things that we've learned over the years, and we've gotten so good at these things that we take it for granted. Okay? So humans are really good problem solvers. So what I like to do is I like to try to break down, abstract how we solve problems into the tools that human beings have to use in order to solve all of our problems. And I break it down into 3 steps. I think that we have to use our memory. We have to ask questions. And we need to be able to use repetition. All right, so let's explore each of these. As far as memory goes, what is your memory? It's our brain. Our brain's a tool, right? What are some of the features of this tool? If you were going into Best Buy to buy a brain, and you were looking at the features on the side of the box, what might it say? By the way, if you go into Best Buy and say you're there to buy a brain, I would expect the police to arrive shortly thereafter. Okay. What would the features say on the side of the box? Storage capacity?
Thinking capacity.
Okay, well, tell me what thinking is. What's thinking?
Imagination.
Okay, tell me what imagination is. I don't dislike where you're going with it, but those things are fairly abstract ideas. But certainly storage, how much crap can we put in there, right? All right.
Clock speed.
I know most of you, this is your first time with me. I'm a little bit different than the other profs.
The speed.
Okay, processing speed, whatever that means. Okay, how fast you can think. Okay, what else? When you think about the brain, what is the brain? What's its purpose? Okay, well, it ultimately delivers intelligence somehow, right? But let's try to break it down into, a set of features. How do we utilize our brain at the simplest, in the simplest way?
Is it like a computer input processing output?
Okay, well, I'm okay with that, but let's think about it from the storage perspective. Okay? How many of you know your name? Funny thing is, we got no hands. Okay, so we all know our name, right? How did you know your name? Well, you learned it in childhood. Your parents kept yelling at you some weird name, and eventually you decide, oh, they mean me. Right? Yeah, like we can't decide one of our cats if she knows her name is Sissy or if it's just Kitty, because we call her about 50%. So, you've learned your name. What does it mean to have learned your name? You've stored it somewhere. So your brain is a storage location for holding information. So somewhere in your brain you have a little, I'm going to kind of start driving this towards computer programming. You have a little name-value pair inside your brain that says, my name is equal to Mike. Make sense? Okay. So all of you have that little storage in your mind, right? You all know your own name. How many of you know at least one other person in this class? Most of us, right? Most of us know at least one other person in here. Even if it's me, you all know me now, right? Okay. So somewhere in your brain, you've stored that person's name, right? So you can think of your brain as just this big, giant filing cabinet with a whole bunch of names and values. What's my phone number? My phone number equals, boom. My name equals, boom. My address is, boom. All this stuff is in your mind, right? That's our memory. So we're able to put crap in. How do we get crap out? When I asked you what your name was, how did you figure it out? All of you knew it right away, right? But how? Well, did any of you think about? Did any of you have to think for a second, what is my name? It was just there, right? Pretty fast processing, right? But what about something that's a little less readily available? Like, how much did I weigh in 7th grade? If you dig, you probably could come up with it, right? Or something close.
It is there, but it's stored somewhere.
Okay, it's stored somewhere, but you kind of have to think. You have to think back. You're almost like crawling your mind, right? To get somewhere close, to at least make a decent guess. I mean, we don't understand the human brain. It's a really complex thing. But what we're trying to do is we're trying to mimic it, and we know for a fact we utilize it heavily to solve problems, right? So what I was really trying to show there is there's some facts that we just get because we use it often. People call you by your name all the time, right? You know what your email address is because you use it all the time. You probably know what your cell phone number is. You might know what your social security number is, the number on your green card, whatever it is, your student visa. These are certain things you might just know because you're having to produce this information often. But any way you cut it, it's just stored in there. And you put stuff in, and then you have to retrieve stuff. But the point is that when I asked you to retrieve your name or I asked you to retrieve your weight when you were in 7th grade, you didn't necessarily say, okay, I'm going to go into retrieval mode. None of us thought about that, right? It just started happening, okay? So how debilitating would it be if you didn't have your memory? What if I asked you to go and walk from the parking lot to class today without bumping into walls, and right off the bat, I'm going to take away your memory? First of all, she's not going to know who she's texting. You wouldn't remember that you're going to class. What classroom is this? This is S120, right? I think it's S120. I teach all my classes in here, so this is my classroom. I just kind of come here. But I'm pretty sure it's S120. By the way, in the future, if you've ever heard a class with me, if it's scheduled in the other room, I'll be here. This is where I come to teach. I think they figured it out by now. They don't schedule me in other rooms anymore. This is just where I go. So without your memory, you would not even get to class. You wouldn't know what a wall is, let alone that you should miss it. Okay, so memory, a very important tool for problem solving. We use it all the time, and we just proven here in the last few minutes that we don't even know how it works. It just does. Heavily rely upon it, right?
Because it's most frequently used.
Say this again?
It is most frequently used.
Oh, well, certainly it's most frequently used, but I wonder mean, obviously, I don't know that anybody's going to answer this, but I wonder, even when we were babies and we started remembering things, I wonder if there was ever a point where we had to knowingly do that, or if we just started becoming surprised that we remembered things. You know, what your favorite toy was or something like that. Like, oh, I like this. What the heck does that mean? My brain says I like this. So I don't know. It's just almost, the brain almost seems like magic, right? It's a tool. We know it's a tool. We know we need it, but it's not really one of those things that there's like an on button. Even though some of us treat it like that, where, you know, we have to fill it with some caffeine in the morning. We figure that's what starts the brain. So actually, I'm a little disappointed. My last class, we had some guys, they brought like big kettles of tea and crap like that in here. You were in that class. What's up? This is a step down. I mean, these guys, they had all these like weird herbs and teas, and they were spiking stuff and giving it to me.
Was it good?
Most of it was. One thing, these guys gave me something, and I didn't. My bathroom schedule was off for about 2.5 weeks. So these guys, they go down to these, like, you know, Arabic or Hindi food stores. Well, no, I'm okay with spice. It wasn't spicy. It was just off. All right. So, in any case, that's our memory. So this is one of the ways we solve problems. Next thing, we ask a lot of questions. Many of the questions we ask, we are aware that we're asking. How are you? In fact, we even ask questions when, you know, out of habit. How many of you asked somebody how they were today? You know, went up to somebody, oh, hey, how are you? We might not even care. Half the time we don't even care. We just do it, right? You know, somebody sees you in the hall, and instead of just being creepy and staring at you, just say, hey, how you doing? Just leave me alone. Okay? So we ask so many questions. It's just habit. We just ask them, even if we don't care about the answer. You know, I don't care how somebody was today. I'm not going to waste memory storage to store that. It's like, well, I happen to know what's his name had a decent morning. Okay, but we ask a lot of questions. Now, back to our example of walking down the hall without hitting the walls. Did you ask questions? We did. We didn't ask them out loud. We weren't probably aware that we were asking them. But do you think as you were walking down that hall, you were constantly asking yourself, am I going to fall over? Do I have to catch my balance with the other foot? How do I walk? Am I going to hit a wall? Am I going to hit a wall? Am I going to hit a person? Am I going to fall forward? Am I going to fall sideways? Constantly, we're having to ask those questions, but we don't know we're doing it. Although, you know, it just happened, right? I mean, in order to miss the walls, you had to ask whether you were going to hit the wall. And even though you weren't aware that you did that, you did. Probably several thousand times between the parking lot and this room. Just constantly. You know, as you're walking down the hall, your eyes are giving you feedback. You're reading in information. You're sampling your environment. And you're constantly saying, am I in the position that I should be in? You know, am I upright enough? Is my left foot going forward? When do I need to catch my balance? When is my center of gravity off enough that I need to take other moves? Make sense? There's all sorts of questions we're asking constantly. And if we were aware of all those, we would go crazy. We'd never be able to shut up, right? What if you had to what if you had to say all those questions out loud? I mean, we're like a multi-processing machine. We're asking multiple questions at once, right? We don't have the instruments to ask all the questions we're asking out loud at once. I need more mouths.
Or am I crazy?
Huh?
I said, or am I crazy?
Yeah, or am I crazy? Yes. So, asking questions is an important way that human beings solve problems. Okay? We remember things and we solve problems in terms of asking a question and responding based on the answer. All right? Lastly, repetition. Think about walking. I like to use walking as that good example. Okay? Well, to solve the problem of walking, we don't put, just to simplify it, we don't say left foot forward, then right foot forward, then left foot forward, then right foot forward, then left foot forward, then right foot. Let's say you had to write those instructions. It would never end. You can't just say walk, left foot forward, right foot forward, right foot, left. You can't just write that over and over and over and over again. Somewhere you have to say, and repeat, right? Put the left foot forward, then put the right foot forward. Now go back to step one and repeat. Make sense? The solution to that problem is of a repetitive nature. Okay? And we can only explain it. We can only create an algorithm or a recipe for how to walk in terms of repetition. Otherwise, it's an infinite explanation. That makes sense? And part of that has to do with our memory. We had to remember step one. That makes sense? Now, you could maybe make an argument that human beings throw a couple other things in here, but I like to abstract it to these three. Okay? The reason I like to look at how do human beings solve problems like this is because of the nature of programming languages. Okay, so everybody's okay with how we solve problems? And we're all okay with the fact that we're really, really good at it, which means we can't explain why or can't explain how we solve problems?
Yeah.
All right, so programming language. What's the purpose of a programming language?
To make the task easier.
Okay, to make what task easier?
For example, the steps which you are following, we are repeating the steps, but we need to memorize the steps, how to follow that one. We are following the, instead of repeating the same thing, we are following the steps which are, for example, if you are following the first left step, and then right step, then left step, you are repeating that thing. So we need to memorize. When you are going the left step, it will be telling us that this time you have to follow this type of gravity, and how much balance you have to make for that, and at what time you need to repeat the same step, and what you'll be facing at the right side and left side.
But do I need a programming language for that? We all got to class today walking. We didn't need a programming language to solve that problem. We just solved it.
To make the task easier.
Well, I think most of you in here are going to agree that you would rather solve the problem as a person than with a programming language.
To make the computer understand us.
Okay. Well, I think there's truth to that. The first thing I would probably say is the purpose of a programming language is to mimic the way human beings solve problems. That is, provide us mechanisms to simulate or emulate these three things. Okay? Mimic the way human beings solve problems with the ultimate goal of telling a computer what to do. Okay? Humans, man, I'm not typing that well tonight. Humans solve. Humans speak natural languages. So I speak English and bad English. Most of you speak English. Many of you speak other languages, right? Arabic, one of the dialects of, isn't there like 5,000 dialects in India? There's Urdu, and then yeah, but then there's like even between those, there's like sub dialects, right? Slangs. But bottom line is, many of us speak different languages, right? But these are natural languages. Okay, what could we say about natural languages? Maybe asking this a little bit out of order, but would you say that when you're talking to another human being, whether it's English or Urdu or whatever language, these natural languages, is there a lot of interpretation that goes on? You're listening to how they're saying stuff to get the meaning, what they're saying, right? It's not necessarily unambiguous. When somebody comes and says hi, just saying the word hi to you could have different meanings depending on how they say it. Like if I came to you and said, hi, that's like, what are you doing here? Right? If I said, hi! Don't you wish you had that on camera? Okay? Okay? Same word, but had different meanings, right? Human beings are expressive, and we like natural languages because our brains are really complex things, and we can deal with that. Okay? We can deal with those types of things. Computers are stupid. Okay? We think of computers as being really smart things. Computers are dumber than rocks. Okay? They only do exactly what our programs tell them to do. And we've already covered this problem that we don't know how to solve problems. Well, actually, that's the wrong way of saying it. We don't know how to tell somebody else how to solve a problem. Okay? It was hard for you to tell another human being how to walk. And I'm brilliant, right? We already just said that human beings, we do this natural language stuff because, well, programming languages are too simplistic. They're not expressive enough for us. We couldn't explain to another human being how to walk. How are you going to explain it to a computer that isn't going to be able to interpret anything? You have to give it literally every tiny little step. Make sense? Okay, so we speak natural languages to each other because it works. Computers can't understand natural languages. If they could, we'd probably figure out how to perfect artificial intelligence or get a lot closer. You know, the best we've done right now is Siri on the iPhone for understanding natural languages, right? You know, but Siri doesn't pick up wouldn't know the difference between hi. Hi! Siri wouldn't know the difference, right? Okay, hi is hi.
Question.
Go ahead.
I think in the future, maybe Siri will be able to pick up those emotions.
Well, I think yes, because we already do have some fields of artificial intelligence can do that already. The question is, can you package it into something small like Siri? I don't think we'll see. At some point, it becomes an ethical as well as a religious question. I'm not sure that, as a scientist, you'd like to think you can perfect AI. But you have to think, even in our example today, as simple as you think some of these tasks are, what human beings are capable of doing, you have to think God plays a role in there. And can we mimic that with machinery? I don't know, but it seems like we understand a lot of really hard stuff in this world, and we hardly know anything about the brain, and there's probably a good reason for that. It's kind of maybe the punchline. But that doesn't mean we can't do a pretty good job of faking it. Yep. There's already some areas of artificial intelligence where somebody's on the other end of a chat, and it's something called the Turing test, where if you can't tell the difference, if you're chatting with a computer artificial intelligence versus a human, if you don't know the difference, then that's considered strong AI. Regardless, it could be that the person who's sitting there is an idiot and couldn't tell the difference, right? Yeah, I don't know. It's. I think there's interesting things like that. So in any case, computers they can't handle natural languages. It's not right for them because they're too ambiguous. Humans like that. We like reading between the lines. Okay, computers need unambiguous languages to follow instructions without any room for misinterpretation. Close? Close enough. Okay? The programming languages we use to talk to our computers, they have to be very, very specific. They have to give us the tools to explain problems, explain solutions in a completely unambiguous way. That's the tool that is a computer programming language. Now you have the person using the tool, us. And we've already covered the fact that we can't figure out how to break our problems down. Even the simple act of getting down the hall without bumping into walls, you couldn't explain it to me. How are we going to explain it to a computer? Okay? So one of the things we have to consider with that is many times the problems we're asking our computers to solve are, in the big scheme of things, very trivial problems. Computers are really, really good at solving very tedious things. That's what we use them for. That's how they're a power tool. And the good news for us as human beings, we don't like tedious problems, right? Let's say that you had, let's say we have 100 million envelopes and 100 million stamps. And I need you to put one stamp on each envelope. Could a human being accomplish that task? A human being can put a stamp on one envelope. Easy! If I handed you one envelope and I handed you one stamp and I said, put stamp on envelope, you could do it. No problem. But now you got to do it 100 million times. Could you do it? Eventually. But then we go back to that whole I might go crazy thing, right? You put 100 million, there's probably some sort of fact there that you put 100 million stamps on 100 million envelopes, something breaks, right? Something goes south in your mind. Now, if you had a machine, and that machine was only designed to take stamp and put it on an envelope, could that do it 100 million times? Absolutely. We love machines that make our life easier like that, right? Absolutely. Okay, so that's really where computers come in. We like computers to solve those types of problems. Many of the interesting fields in computer science and IT really deal with having computers solve more humanistic type problems. Computers playing chess, which becomes a math problem, but what are we doing? We're trying to teach a computer to think like a chess grandmaster. Okay? Thinking 20, 30 moves ahead. All right? So, we're taking something that a human being, how many of you, many of you at least know how to play chess probably. And really good chess players, what do? They are thinking 2 or 3 moves ahead. Okay? The great chess players might be thinking, I don't know what it is, it's like 7 or 8 or 9 moves. A lot of moves ahead. But what they have to do is they are using their memory to store a whole bunch of different states of what that board, the chessboard, might look like. Eventually, a human being can't hold that many things. Right? If I start telling you to remember numbers, if I told you to remember the number 3, I'm going to ask you about it after the break, most of us could probably retain the number 3. Okay? If I ask you to retain the number 3 and 17, we still have a pretty good fighting chance. But pretty quickly, I could give you enough numbers to remember that we're going to start forgetting numbers. Right? Okay? These chess players have to remember the entire state of the board, taking into consideration what their opponent might do. All right? So, great chess players are really showing some amazing feats of memory and problem solving at the same time. Well, is it really a wonder that we could build a computer that could beat the grandmasters? No, just put more memory in it. We'll just store every single possible state of the board and we will solve the problem of chess. This guy plays perfect chess. So, it's that's not artificial intelligence. That's a brute force attack, or brute force approach to solving a problem, because computers can do that because they have lots of memory and they can do things very quickly. A human being, if you had a gigantic book of all the possible states of a chess board, even if that's given to you as information you're allowed to use, we wouldn't be able to process through that fast enough on a per move basis in order to put it to good use. So computers can do that stuff as well. So I really want you to think about the different things that computers do for us versus what humans do. We're really solving different classes of problems. Okay? Computers aren't better than us. Okay? We're amazing. And one of the things we have to do is we have to know what our limitations are and really know what the limitations of a computer are. What the limitations of a computer are. What things does it make sense for us to ask a computer to do, and what things does it make sense for us to do on our own? If you ever watch one of those TV shows like How It's Made, something like that, I like that show. It's on, they usually do like marathons somewhere between 10 p.m. and 4 a.m. or something like that. So if I can't sleep, I'll watch that. It's always amazing when you watch manufacturing plants, and there's certain aspects of things that are automated, and other aspects of things are done by hand. I'm like, why would they do that by hand? And there's usually some sort of reason that we just can't build a machine that doesn't damage the packaging or something like that. There's certain things that just can't be solved reasonably by a computer or by a machine. So what we want to do is, as human beings, as problem solvers, we want to extend our problem-solving ability by being able to leverage machines, being able to leverage computers to help us solve large classifications of problems, but not necessarily to solve every problem. I always think it's funny when any of my buddies who know what I do, like, well, it'd be cool if you wrote a program that, I don't know, cooked spaghetti or something. Well, what's spaghetti? I'll just cook spaghetti. I don't need a machine to make spaghetti. So, it's something for us to consider. So anyways, programming languages, these guys attempt to mimic the way human beings solve problems with the ultimate goal of telling a computer what to do. So a programming language attempts to give us tools necessary to emulate these three things. And let's say, and then some, but these three things at least. Okay? So, the mapping is this. Memory, for humans, is equal to something called variables in programming languages. Okay? In any programming language. I know a couple of you said you've had certain languages and stuff like that. One thing I want you to kind of get out of your mind right now is, generally speaking, there's no such thing as saying, I know C#, but I'm not good at Java. Or, I'm good at C++, but PHP just confuses me. Okay? Programming is programming. It is a mindset. Okay? The way you solve problems using a programming language has everything to do with what we've talked about up to right now today. The language itself is just syntax. And think about this in terms of natural languages. Okay? I'm a human. I speak natural languages. I only know English and bad Spanish. 2 semesters of high school Spanish. Not really Spanish. I could barely order at Taco Bell. Okay, so I speak English. But my thought process when I'm communicating with another human being, that idea of natural languages, the problem solving of talking to another person, goes beyond English. If I were to learn the syntax of Urdu, I could talk to somebody in that language because the mindset, the way you think about talking to another human being is the same. You're just accomplishing it through a different syntax and a different set of noises. That makes sense? Okay? So we all already know how to communicate with people. We just have to agree upon a language. That makes sense? So I might not know all the languages, and you guys might not know all the languages, but as long as 2 human beings can agree upon a language that they both know, we can talk to each other with the same mindset. Programming is the same thing. Okay? There's a problem-solving approach to programming. When you're talking to a computer, as opposed to talking to a human, you have to go into a different mode. Okay? We know when we're talking to humans that they're going to be able to fill in the blanks. They're going to be able to figure out what we meant. Okay? They'll be able to correct us when we misspeak. Right? We do that all the time. You mean one thing, but you say something else, and they know what you're talking about because what you said didn't make any sense. Right? We do that all the time. But it's not that big of a deal because human beings can fill in the blanks. And it's not a big deal. Computers won't do that for us. If we tell it to do something stupid, it'll do that stupid thing. That makes sense? So we need to change our mindset when we're trying to talk to a computer rather than a person. That's the programming problem, okay? Not the languages themselves. Okay? The programming problem is understanding that we can solve less complex problems on a computer, and it's really geared towards those tedious problems, but also that when we're explaining something to a computer, we can't rely on it to fill in the blanks or to figure out what we meant. We have to tell it specifically and exactly what we mean. That make sense? Okay, that's what's hard about computer programming. We're very good at talking to other people. Most of us are not very good at talking to computers. We're inexperienced. Make sense? That's what's going to challenge you in this class, is that process. The fact that we're using Java as the language, it's all the same crap. You know, we'll talk about it here in a few minutes, but the difference between these programming languages is little. It's like the difference between American English and British English. I can go over to Britain and I can hold my own. Okay, I can go to Canada and I can hold my own. Unless I go to French Quebec. Okay. Most of them speak English there too, to speak to the dumb Canadians and the really dumb Americans, right? Okay, but even though they have a couple of different words, especially the Brits, right? The Brits have some replacements for a lot of words that Americans have. We're speaking the same language. Just have a couple little replacements here and there, but we can get by. Differences between programming languages is much more like that than it is like English versus Urdu, okay, or English versus Chinese, okay. Those are, from my perception, huge leaps, right? Even though they're both natural languages, there's a whole group of syntax that has to be learned, and programming languages in many cases are based off each other. There's like a natural lineage. So, I think it's not going to be that bad as long as you're going in with the correct expectations. Okay? So, punchline there is, don't be afraid of the language. Programming is programming. Focus on the problem-solving aspect. Focus on, I need to learn how to talk to a computer. And the fact that we're using Java as our tool to talk to the computer just happens to be the choice we made. For decent reason, but the choice we made nonetheless. Okay, so the way human beings solve problems through memory, a computer programming language mimics that through variables. Similarly, asking questions. So human beings solve problems by asking questions. These are mimicked through something called conditionals. Typically, I'd say these are if statements. There's actually a kind of another structure for conditionals called a switch, but nobody uses it. It's really too limiting, in my opinion, the switch, and there isn't a good reason to use one. But it does exist. It's fair enough in this slide to say if statements. Okay? Finally, repetition. This is done through loops. Okay? Every single programming language that you will ever run into will provide a construct for storing things in variables. It will provide a construct for asking questions through conditionals. And it will provide a construct for repeating steps through loops. 100% of them. Okay? That's a programming language. Down to those little things. Okay? Now, I like this next group of slides. There are 3 types of programming languages. Machine language, low level, and high level. Let's talk about machine language. That's the computer. What language does the computer speak? Binary, zeros and ones. Okay? How many of you speak machine language? Yeah, we're talking about how our challenge in here is going to be communicating with a computer. How about I give you the little 2-button keyboard? We'll plug it in. Just tap out our conversations, right? You've seen the TV show, kids cartoon Futurama? Any of you in here seen Futurama? Sometimes cultural differences, you miss out on some of the cartoons. It's on Netflix, if you watch it on Netflix. But there's it's placed in the future, whatever, but there's a robot in the show, his name's Bender. And one of the jokes in the show is sometimes Bender puts on these plays where he speaks binary. His lines in the play are 1001110110011, and the other robots are watching it and getting all emotional, because they know what it means and that kind of stuff. Okay. So human beings we don't do the zeros and ones. We respect the zeros and ones. We respect binary logic, but zeros and ones, a little bit too abstract for us. Okay? So then we have our low-level language. But before we could talk about low-level languages, we need to talk about the CPU. What is the CPU? Okay, that's always the answer, right? I ask what something is, you tell me what it stands for. So that's Central Processing Unit. What did you say? Heart of the computer. That sounds so poetic. The heart of the computer. What does that mean? What's the CPU? What does it do? Processes crap? What does it mean to process crap? Can our computer work without a CPU?
No.
Well, why not? We could save a lot of money if you're building a computer. You just skip the CPU. So what does it actually do for us?
Interprets. It interprets the high-level language and it delivers it to the computer so that the computer can understand what we mean.
Okay, I think we're getting pretty close there. So really, the CPU knows how to. It's like a magician. It knows how to perform a whole bunch of magic tricks. Okay, I like to refer to them as magic tricks. So the CPU has a list of tricks that it knows how to do. All right. So when new CPUs come out, in the old days you had the 286 SX23 or 33 megahertz processor. Then you had the 386s and the 486s. Then you had the Pentium processor. Then you had the Pentium 2 and the Pentium 3 and the Pentium 4. And they threw some Xeons in there. Then you had the Core Solos, the Core 2 Duos. Now you have the Core i3s, Core i5s, Core i7s, and now you have the new bridges in those and all these different architectures. So as each new processor comes out, it's a superset of the previous processor. Okay? So if you go back to one of these old processors, the x86, 10 megahertz processor, it knew how to do this many magic tricks. Just a handful of magic tricks, let's say. More than a handful, but let's just use that for the example. Okay? Then the 286 processor that came out, it knew how to do 5 times more magic tricks, but it knew how to do all the originals. Okay? Went back to magic school, learned new tricks. Then the 386 that came out, it was a superset of the 286, which was a superset of the x86. So what we have today with our newest, latest, greatest, coolest Core i7 processors from Intel is we have something that's a superset of many generations of CPUs, right? Now, these magic tricks that I'm referring to are a whole bunch of things. They're little tiny, I guess they're They are minimalistic moves that when put together in a certain order solve a complex problem. Okay? Typically processors, the magic tricks that a processor knows how to do, that a CPU knows how to do not accomplish very much in and of itself. You have to put together 2 or 3 or 4 or 5 magic tricks in a row, and then all of a sudden something real, something meaningful happens. Okay? So our CPUs are designed in such a way that they have a list of magic tricks, and that is what Intel has decided that large categories of problems can be solved in terms of these magic tricks. If these magic tricks are called in a certain order at a certain time, something good will come out of that. Okay? So what a CPU does is you tell it what magic trick to perform, and it performs it. And it comes back and asks, what next, master? Okay? Just doing our bidding. All right, so CPUs perform the magic tricks that we tell them to perform. If we tell them to perform the right magic tricks in the right order, some problem may be solved. That make sense? Okay? That's what the CPU is. And CPUs, for this argument at least, are machine language. Okay? They speak this language. Now, a low-level language is a human readable language that has a one-to-one relationship with the magic tricks on the CPU. So every line of code we write in a low-level language translates to exactly one magic trick the CPU knows how to do. Okay? So, for instance, we're going to say you're a CPU. Okay? Now, instruction 0001 inside your mind is the jump instruction. Okay? So, I'm going to say jump. That would be like in a low-level language. And that jump gets mapped to instruction 0001, which you then execute, which causes you to jump. That make sense? Okay? I said jump, he heard 0001. Make sense? That was the instruction number for what I meant by jump. Okay? So, now if I was telling him how to walk, I might say left foot forward, right foot forward, left foot forward, right foot forward. And maybe that's instruction 0001, 00010, 00011. Something like that. Okay? So I'm just going to keep feeding you these instructions, and then we're going to go back to the previous one and repeat it. Make sense? So, a low-level language is human readable and writable. So let me throw in writable. Okay, so it is English-like. And it has a one-to-one relationship with the CPU. Now keep in mind that as I've advertised, CPUs have a whole bunch of instructions that are meant to be very granular, very small, where they're only a little tiny piece of the solution to a problem. So chances are, if we want to solve a problem that has any sort of complexity to it, we're going to have to put many instructions in a row together. Hundreds or thousands of instructions in a row to actually accomplish something meaningful. Make sense? So even though we're not dealing with zeros and ones, if a human being was writing code in a low-level language, we're still writing a lot of instructions. Okay? I'm marching behind him, telling him left foot forward, right foot forward, except the dude standing between us that's doing the translation saying 0001, 0010, and he's just executing and executing and executing, right? Okay, so it would get pretty tedious. So even writing software in a low-level language, which is doable by human, is tedious. So we get to our high-level languages.
Excuse me.
Yep, go ahead.
For the low level language, for example, can we consider assembly?
Assembly would be a low-level language. Yep. Yeah, I usually do an example slide, but that's fine. So this would be like assembly language. All right, so high level is a human readable / writable language that has a one-to-many relationship with the magic tricks on the CPU. Humans really like this one. Okay, we write one line of code and it translates somehow. We'll talk about that, what that somehow is in a little bit, but it translates somehow into a whole bunch of instructions, a whole bunch of magic tricks on the CPU. We like power tools, right? One line, maybe it's 300 instructions. Cool. Okay, that's our kind of language, high-level languages. Now, that isn't to say that low-level languages don't still have a place. All right? We'll come back and talk about what that place might be in a little bit when we get to the next slide. All right, questions on this one?
Examples for high-level language.
I'll give you some examples. See, the issue with giving the examples right now is my next slides are like the same kind of slides, but here, we'll throw a couple out there. So we got Java, C++, C, C#. A lot of the languages you've heard of are high-level languages. Throw PHP in there, Visual Basic, whatever.
Excuse me.
Yep.
You said one-to-many relationship. What does it mean?
Every one line of code I write in a high-level language translates to many instructions on the CPU, as opposed to low-level, where I said jump, it translated to instruction 0001 for him. In a high-level language, I might say run. And run would translate into maybe 200 instructions that he understands that make him run down the hall. That make sense? But just by me giving that one command. So high-level languages are very powerful for us. Okay? And it's really that translation. Those Intel processors, the CPUs, they're designed with all those magic tricks to be very granular so that many problems can be solved in terms of a whole bunch of those magic tricks. We don't want one of those magic tricks to do too much, because it might mean that we can't solve a certain problem because it does too much. That make sense? For instance, if I only wanted you to take one step forward, but we only had the ability to take 2 steps forward, I made it do too much. You see what I'm saying? So the idea is they try to make the magic tricks the CPU knows how to do. They try to make them as simplistic as possible, so that they're only a little tiny widget, a little tiny cog in the bigger solution. So when we write that low-level language, we're having to tell each cog how to turn. Do this, then 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 this. With the high-level language, we can abstract that and say, I want you to run down the hall. Do what it takes. Okay? But something in the middle needs to solve that problem for us. Okay? Somebody has to get a low-level language out of this. The high-level language doesn't just magically work. Okay? And that's where we get to our next slide. There are 2 types. Two types of programming languages. Now, for each of these, even though the slide titles look pretty similar, each one is through a different lens. We're looking at this one through the lens of the different languages in terms of how the CPU views them. This one, we're looking at it from a software perspective. So the 2 types of languages we're going to talk about here are interpreted languages and compiled languages. Interpreted and compiled. Okay, let's talk about compiled first, so that closely relates to what we were just talking about. Okay, a compiled language is typically a high-level language that uses a tool known as a compiler, which translates high-level, translates a high-level language into a low-level language. Okay? So we have this piece of software known as a compiler. It's a tool that somebody had to write. Somebody had to do all the tedious work in that low-level language. Okay? So that human beings today could use high-level languages. So back to our example, I said run. And the step we skipped is the compiling step. What the example we use is you just started running down the hall. You're the CPU. Okay? But what I really needed is I needed our compiler over here. I said run in a high-level language. Now what you're going to do is you're going to translate that into the 25,000 lines of code, low-level code, all the magic tricks in the correct order that he needs to follow in order to accomplish the act of running. That make sense? That's what the compiler does. All right? So in order for a high-level language to ultimately give instructions to a CPU, we need a compiler. All right? Because human beings like speaking the high-level language. CPUs like speaking machine language. All right? But we can't rely on the CPU to do the translation for us. So we have this piece of software known as the compiler that does it for us. All right? Now, having said that, this all happens prior to runtime. That is, my high-level code was translated into low-level code by the compiler before we ever asked you to start running. Okay? So when I actually finally executed the program that I wanted you to do, we already had your 25,000 lines of instruction. That wasn't happening while you were waiting. I wrote my high-level program once, then I immediately sent it to the compiler. And he did the job of giving me all those lines of code that when I actually want to execute this program, I'm going to give to the CPU. Okay? That makes sense? So we're not having to delay the CPU. We're not hurting our performance by waiting for you to get instructions one by one from him. Okay? He did all the work up front before we ever asked the CPU to do anything. Okay? And it'll make sense when I get to the interpreted version. Okay? The alternative to this an interpreted language is typically a high-level language that uses a tool known as an interpreter, which translates a high-level language into a low-level language in real time. This is during runtime. Okay, so now let me give you real-world examples of these to clarify between these two. So let's say that the president is giving a talk. All right, so he's up there, he's talking about some policy issue or something like that. And you have somebody on stage who's an interpreter. Maybe you have somebody up there who's converting it into sign language. Maybe somebody else who's speaking it in German. Okay, so as the president says each word, the interpreter, while the president is currently speaking to the audience, the interpreter is turning that word into the equivalent word in sign language or the equivalent word in German. Okay? That's an interpreted language. While the president is talking to the public, there is somebody else who is taking what he's saying and turning it into something that's usable by this group over here, usable by the CPU. Okay? So if you were deaf and you speak sign language, okay, President's here moving his lips. You're getting nothing out of it. Okay? So you're the CPU in this example. Okay? So you're the deaf person who needs the sign language. This guy over here, he's taking what I'm saying and doing the sign language stuff that now you're able to understand. Okay? But you're probably going to be a couple of words behind me. Okay? Because I'm saying it, then he's interpreting it, and then you're getting it. Okay? That's an interpreted language. The compiled language is this. You're on a news show. Okay? The president speaking right now. Okay? But this news program, the German news program, was given the script from the president's speech a couple of hours ago. And they went through and they translated it from English into German. Okay? Now, while the president is speaking, they maybe have it kind of in, the volume turned way down in the back. The German newscaster is reading the president's speech in German while the president is doing his own talking over on the side. The fact that the president's even there doesn't mean anything. The German-speaking audience is hearing about it at the same time as the president's talking, in real time, during runtime, in German, because it was translated from English to German 2 hours ago. That makes sense? You're not being delayed. You're getting it in real time. That's a compiled language. Compiled languages, we write the code and translate it before we ever run it. Interpreted languages, we write the code and we translate it while we're running it.
Wait. One more time. You say
Okay, yep. Compiled language, the second one. We write the code and we translate it before we run it. Interpreted languages, we write the code, but we translate it while we are running it. So interpreted is, I'm speaking as the president, the sign language guy's converting it in real time, he's getting what I'm saying 2 or 3 words behind. Okay? Because during runtime, while I'm babbling, this guy's interpreting my words so that this CPU can understand it. Make sense? Compiled languages, the German newscaster got the script 2 hours ago. They had their translator guy turn it into German, and he's sitting there reading the German, maybe even started 5 minutes before the president started. He already had it, right? And that makes sense? Okay, so that's the compiled version of it. Now, the thing I want us to think about with each of these, and this is relatively slow. This is relatively fast. Okay? I want us to think about interpreted languages as being relatively slow languages. And I want us to think about compiled languages as being relatively fast languages. The reality is they're all fast. Computers are really fast. Okay? So for many applications, we wouldn't know the difference between an interpreted and a compiled language. Okay? Really where it comes into play is in this discussion, probably video games is the best example. When you're playing video games, typically, especially when we talk about the grown-up video games, the shoot 'em up, war ones that have a zillion things happening at once, this kind of stuff, as opposed to Angry Birds. Angry Birds is not a real complex game, but I'm talking about the big crazy games. These need to be very fast, right? Okay, so we're probably not going to want to tax a computer. We don't want to have an interpreter sitting here while we're playing this game in charge of making sure the game is coming to us quick enough. We want to handle all that interpretation beforehand. We want games to be written in compiled languages. Okay? But maybe a business application. Microsoft Word, something like that. Maybe that could be written in a interpreted language and be okay. Our computers are really fast today. So it's not like you sit down and you're like, well, I'm going to need a little bit more horsepower in order to be able to run Microsoft Word. You know, you need to have a pretty old computer for that to really start becoming a problem, right? But if you go out right now and you buy a game that came out in the last 3 months and your computer's 6 months old, you might have to turn a couple of the settings down. So I mean, that's actually another interesting thing about software development. Many times these giant games, I mean, these things took 2 or 3 years to write with a team of 30 or 40 or 50 programmers. Okay, there's millions of lines of code. Well, when they started writing that game 3 years ago, they had to make a guess at what technology would look like today. Make sense? So they were having to say, well, how much faster will stuff be then than it is now? So they were really writing something that wouldn't run on what they had then. And a good example, I was actually mentioning at one of my classes earlier today. If I'm ever in a bad mood on Wednesdays are a very long day for me. I've been here since 7 a.m. Although you've probably been here most of the day too. But what does she know? She actually works for a living, I don't. I sit up here and babble. Okay, but anyways, in this class I was, we were talking about a certain game. I just had it. Now it's, I think it's called Cryo. It might come to me in a few minutes. It's not a big deal, but it's kind of famous. It came out about 3 or 4 years ago, and it was one of those examples of a game that took 3 years to design, and they missed their mark. That is, when it came out, there really wasn't any hardware that could run it. Like basically, even the best hardware that was out that day had to like turn the settings of the game like way down in order for it to even like function. You know, now the reason it came up is he plays it now, and he could play it plenty fast. You know, this was 2 or 3 years ago. Modern graphics cards, they do a very good job with that game now. So they kind of missed the technology by 6 months or a year. You know, it came out. It was pretty. it was a pretty rough program for modern, even expensive gaming machines to run when it first came out. So, kind of an interesting thing. What's this? No, it was a first-person shooter, and it was like Cryo or no. It's gonna pop into my mind in like 20 minutes. As soon as it happens, no, it's like what I'm saying. It's like, you know, Cryo. It's something real short like that, and it starts with a C. No. Real short, something like Cryo, but I think I'm missing a couple of letters. I promise it will pop into my mind. That's it. All right, so interpreted, relatively slow. Compiled, relatively fast. Okay, but don't be afraid of interpreted languages. Our computers today are really fast.
So why they use interpreted language?
Well, you also have to consider that programming languages have been around for a long time, and computers keep getting faster and faster and faster. We've kind of slowed down on how much faster computers keep getting. We keep just adding more cores now, right? So if you look at the speed of our processors today on a single core compared to the speed of our processors 5 years ago on a single core, they are faster today because of the architecture. The architecture today is better. So you really can't just compare the gigahertz. You can't just say, well, it was 3.2 gigahertz then and it's 3.2 gigahertz today, because the architecture of the, think of it like a sports car. They both might, both sports cars might have 300 horsepower, but maybe the newer one has some modern things in the engine that allow it to squeeze some extra speed out of it or something, something like that. So you really can't just look at the numbers, but if you look at the last 5 years and compare it to the 5 years before that, computers have sped up much less on a per core basis in the last 5 years. But what we've seen in the last 5 years is we've gone from dual core to quad core. Now we have CPUs with 6 core. We have machines with dual 6 core processors. And those a lot of times have something called hyperthreading, which is effectively 12 cores in each of those processors. AMD, which is kind of going out of business now on their CPU side, but whatever. They, I think, have an 8-core processor. But, the point is that more cores isn't necessarily better. It sounds cool, right? The example I usually use is, it goes back to the joke of how many people does it take to change a light bulb. Okay, so let's say that the speed that I can change a light bulb is 10. Okay, 10 is the fastest you can change a light bulb. Okay, I can change a light bulb at speed 10. And I'm going to compete against this entire half of the room, all you guys. Okay? You guys can each change a light bulb at speed 9. It's a little bit slower than me. Okay? So I'm over here with my light bulb. You guys are over there with your light bulb. We're each changing one light bulb. Who's going to win this race? I am. Who cares if you have a football team? It takes one person to change a light bulb. Okay? That task can't be divided up. That makes sense? So the fact that my 1 core is faster than any of your 1 cores means that I'll win that race. But let's say that we were cleaning up a park. Okay, and I can clean up a park at speed 10. And each of you guys can clean up a park at speed 7. Individually, you're substantially slower than I am. But as a team, you guys are going to be able to cover that park much more effectively than I will. You would beat me by a lot. Okay? If we were comparing this to real life, probably by many hours, depending on how big the park was, right? Okay? That's the type of problem that multiple cores lend itself to, where work can be divided. Okay, so we've kind of hit a wall in technology where we just keep adding more cores because it sounds better. So if you're ever shopping for a machine, you got to consider what you're using it for, because getting the faster processor may not get you anything. You're almost always better off having enough RAM and getting the faster hard drive. Save your money. Don't spend too much on a CPU because you probably won't use it. It's not spelled right, is it? All right, I was testing you. You all failed. Okay.
You have the time.
What's up? I still have a typo?
The compile, which translated.
It's a compiler. Which translates. Yeah, there we go. See? I was testing him. It's a star for the day. All right. So, 2 types of programming languages, interpreted and compiled. There are 2 types of programming languages. Which one do I want to do here? Domain specific and general purpose. Domain specific programming languages are languages designed to solve a very specific class of problem. For example, HTML is a domain-specific language. So HTML is the language for making web pages, right? Arguably, you could say it's a programming language. I think that's fair. It is an interpreted language. It's interpreted by a web browser. Web browsers know how to read HTML and spit it out in pretty pictures and text and stuff, right? Okay? But HTML, in comparison to other languages, is a very small language. You can learn HTML in a weekend because it's not trying to solve all the world's problems. HTML is just trying to solve the problem of making web pages look pretty. It's a text and graphic formatting language. So it's solving a very specific domain. Make sense? So we have programming languages like that. Okay? Interestingly enough, the reason why I say arguably HTML is not a programming language is if we roll back here, HTML does not allow us to remember variables. HTML does not allow us to ask questions. HTML does not support loops. To add that ability into web pages, what do you have to use? JavaScript. Okay. PHP would be on the server side, but on the client side, if you don't want to have the internet or anything. So HTML itself, by what I've taught you, I could argue is not a programming language. Okay, I could argue it's a data representation language. Okay, but HTML plus JavaScript, which all of your web browsers know, all your web browsers understand, those two guys together, we could say that JavaScript augments HTML to make it a programming language solution. Make sense? Okay, but HTML itself is domain specific. JavaScript, it sits between these two, but probably closer to general purpose. And we'll talk about general purpose here in a second. These are languages designed. See, told you I was tired. These are languages. Good thing human beings speak natural languages, so you can interpret. Interpret what I meant, not what I wrote. Okay. General purpose are languages designed to solve a large classification of problems, or a general classification of problems. Okay, so these are languages meant to solve all sorts of stuff, not formatting text, not maybe there's a, let's see, how many of you ever worked with those Lego Mindstorms? You know, I'm talking. I think artificial intelligence class deals with it. It does. So the Lego Mindstorms, which are like little robotic stuff, it has its own programming language that's domain specific for doing Lego Mindstorm stuff. Okay, it gives you the ability to tell that robot what to do, but those robots can only do a very specific number of things. Okay, like detect a wall, turn left, turn right, those types of things. So you couldn't use the Lego Mindstorm language to write an operating system. It doesn't do enough. Okay? So that would really be a good example of a domain-specific language. As opposed to general purpose languages like C++, Java, C#, blah, blah, blah. Okay. These are languages that are used to solve any problem that could be solved by a computer. Okay? So these languages tend to be much larger in scope. For example, I've been, let's see, when did Java come out? 94? So I've been programming in Java since 1994. And I would guess that I know, I would say definitely less than 20% of the whole language. Because I only know about the stuff I've used, right? I mean, Java has its core language, you know, the stuff for creating variables, asking questions, doing loops. I know all of that stuff, okay? But surrounding that are a zillion libraries to solve all sorts of problems, things that are built on top of the language to solve larger classifications of problems. Now, could I just write those things on my own if I needed them? If I didn't know about them, sure. I could use Java's core language to implement my own solution to this problem. You know, just like if I need to do something around the house, I could make my own tool to do it. You know, you can fix anything with a screwdriver, right? Or I can go to Home Depot and buy the right tool. You got options, but you don't know what you don't know. So if I need to solve a specific problem, the first thing I might do is I might go to a web resource and determine, does Java have a solution to this built in? If it doesn't, I'll write it myself. If it does, maybe I'll utilize the one that's already there. Okay? Now, word of advice. the stuff that I have you do in here, first of all, you can only solve your problems in this class in terms of what I've taught you in class. Sometimes I will teach you something. We are purposely doing it the hard way so that I can introduce the easy way. Okay, so you can only do it in a way that I've taught you in class. So if you've had some programming experience or something like that, when you've done your homework, when you're doing your homework, think about what we've introduced in class and only solve things in terms of that. Because the problems I'm giving you are on purpose. The order I'm giving it to you is for a reason. Okay? So having said that, these languages like Java, they're so large that even if something's built into the language, you might choose to implement it yourself. Because let's say, an example, those of you who had 537, the data structures class, let's say we're having to use a linked list. Well, there's a generic linked list class built into Java that does a whole bunch of linked listy things. Well, if I just need to create a very simple, singly linked list that only needs to store certain kinds of things and only needs to add stuff to the front, maybe I'll just write it myself real quick. It'll take less time than manipulating the more complex one that's built into Java to do what I want it to do. Make sense? Okay, so the core language of Java isn't that big. But these other libraries leverage that core language. So you should think about these high-level general-purpose programming languages as kind of like the when you go to Home Depot and you buy that box of the 140-piece toolbox, that people get for Christmas presents and stuff like that. Okay, which has a large grouping of tools that could be used for a lot of different things, but not everything. Okay, if you were going to build a house, you might need more than the 140-piece tool set. Okay. I say might. You get the right type of temperament and probably a guy. He might convince himself he can build a house with a 140-piece tool set for juniors or something like that. But, the punchline is that's very much the example of a general purpose language. You start off with a core that's that 140-piece toolkit, and then you have Home Depot, which has all sorts of things that add on to that toolkit. Okay? So that's domain specific versus general purpose.
You said the domain specific language could be learned within some weekends.
Say this again?
You said the domain specific languages can be learned within some weeks, right?
Well, I mean, HTML is a reasonable example, except I'm arguing that maybe this isn't really a programming language. If you want another example, the one I gave was the Lego Mindstorm. Mindstorm. They should have called it Windstorm. It sounds better. Okay. Lego Mindstorm language.
All of them are high level.
Not necessarily. These are general purpose languages are typically high level. Domain specific. I guess I'd say this. Domain specific or general purpose does not dictate whether it's a high level or a low level language. But generally speaking, they would all be high level languages. But these don't really have anything to do with whether they are high level or low level. This is really a trait of a programming language. Okay? And we'll kind of put all this together at the end. Yeah?
You said that JavaScript is more likely general purpose, but not general purpose. Why?
Well, I think JavaScript is general purpose. If I had to put it in one of the categories, I'd say it's general purpose. Realistically, the reason why you might say it's kind of in the domain-specific category is because you really only use JavaScript as it relates to web pages. That was completely true probably 15 years ago. It's less true now. A lot of places are using JavaScript for like scripting language built into it and things like that because of its general purpose nature. So it's it's fair to call it general purpose. Maybe the better way of saying it, it's only fair to call HTML domain specific if we attach JavaScript to it. If we say HTML/JavaScript. because JavaScript itself is a general purpose language. It does have some webby type things built into it in terms of accessing the document on a web page, but that doesn't automatically make it domain specific. That's kind of like what I was saying with Java, where there's some extra libraries that allow you to do some more complex things that you might not want to have to write on your own. Well, yeah, sure. Yeah, jQuery. jQuery it's one of those buzzwords, and all it is a specialized JavaScript library, right? So it's the same thing. It has to do with rewriting the document. Okay, but you're right. You're right. I mean, JavaScript is general purpose. Interesting thing to throw in there, though. JavaScript has nothing to do with Java. They're not even related to each other. Not even third cousins. So, just happens to be the same name. There's probably a reason behind that. I'm not sure what it is, but they're not based on each other. They're both based on the same parent language. We'll talk about that here in a little bit, probably after our break. But they're both based off of C. Same parent language.
Just interest about JavaScript is, I don't know if you see that they built a Unix system just in JavaScript.
Okay, that runs in a web browser or that runs in an interpreter?
In a web browser.
Okay, so a whole Unix operating system that loads and launches out of a web browser.
Yeah.
That's interesting. Actually, that would have been a very interesting problem because they would have started running out of some of the memory constraints that the web browser puts on them. Yeah, that's actually interesting. Yeah, they use JavaScript to write a Unix operating system that ran in a web page, ran in a web browser. Yeah. But you have to, and that's actually related to what we're going to talk about here in a little bit, probably after break, dealing with virtual machines. I mean, because at that point, you're not writing your program to run on this general purpose computer. Your program is running on a web browser, which is a subset of what that computer is capable of doing. See what I'm saying? So you're having to write this program in terms of what a web browser is able to do. The amount of memory that was allocated to that web browser, the amount of CPU time that's allocated to that web browser, the way that the web browser can allow for various inputs and outputs. With a web browser, you're not dealing with the whole general purpose, the entire feature set of a computer. You're just getting the feature set that's part of that program. So, yeah, interesting stuff. Okay, so that's domain specific versus general purpose. Just want to get through these last couple, and then we'll take a break. We're almost at a natural stopping point. There are two types of programming languages. Actually, I'm sorry. Three. This slide's three. Three types of programming languages. Three types of programming languages. We have functional, procedural, and object-oriented. All right. Functional languages are languages whose features are encapsulated within specific functions that, when used in a certain order, solve problem. It's fair to say that many functional languages they may be domain specific, or at the very least, less than completely general purpose. Okay? Functional languages, they're a little bit of a hard thing to explain because they really aren't that prevalent. I can list several of them pretty quickly, but they're not mainstream languages. The example I usually like to use is, for those of you, we all know what a graphing calculator is, right? So you have a graphing calculator, probably made by Texas Instruments. They're the graphing calculator people anymore, right? Okay. On the Texas Instruments graphing calculator, it has a programming language. And that programming language is defined as a functional language. What I mean by that is, when you're typing things into your graphing calculator, you are solving problems in terms of sines and cosines and tangents and integrals and derivatives. These are functions built into it that if you say the sine of 40 plus the tangent of 30 minus the something else, you get a final answer. So each of those functions has a bunch of magic behind it. And if you provide it with the right inputs, it will do its magic. Okay? But functional languages tend to take the opposite approach to kind of what I was talking about earlier with our CPU, where the CPU can do a zillion different magic tricks and tries not to do too much at once. Functional languages typically have at least some domain in mind when they're written. That is to say that when they create those functions, they make the functions do enough so that you don't have to call too many functions to accomplish what you want. Okay? So if you want to take the sine of a number, you don't have to call 20 functions to get the sine. You can just call the sine function. That make sense? Okay, but it does typically have a domain in mind for creating those initial functions. And then beyond that, you can create your own functions in many of the languages. Examples of this would be Lisp, Scheme, Prolog. All three of these are artificial intelligence languages. They have things built into them specifically bent towards solving some artificial intelligence problems. Okay? Functional, say this again?
VLSA?
VLSA? Yep, true.
Can we consider HTML and CSS as functional?
No. Let me backtrack. Definitely not HTML, because I'm not sure we can even truly call HTML a programming language. And that's not really a knock on HTML. It's really a compatibility with my definition of programming languages. I mean, if you read a lot of textbooks, I haven't seen somebody else explain programming languages the way I do, using these 3 ways of problem solving and things like that. I happen to think this is a very good way of doing it, otherwise I wouldn't do it. But given my definition of a programming language, HTML probably gets disqualified because it's just not compatible with my definition. Really HTML fits much better into a data representation language as opposed to a programming language. So it would fit into the same categories like XML and JSON, other data representation language. Perfectly important, perfectly good, but not a programming language. Make sense?
Can you repeat the explanation again, the functions?
What, for functional languages?
Yes.
Sure. Well, first thing, let me say this. I am probably not going to put very much importance on functional languages in here. They really are fairly rare, and they really are very specific to certain things. And they are difficult to explain. Okay, so it's if it seems a little fuzzy to you, I think that's okay. Let me explain it again, though. Like I said, the best example I like to use is the graphing calculators. But so you have this. You use a graphing calculator to solve math problems. So the domain you're applying that calculator to the problem of math. Okay. So built into the language of the TI Texas Instruments graphing calculators is a language of a whole bunch of math functions. Functions for solving the sine and the cosine and the integrals and the derivatives and tangents and all sorts of stuff like that. Taking certain things to powers, okay? Calculator type functions. And when you solve a problem, you're solving a math problem in terms of those functions. So your lines of code are going to say, I'm going to call this function, then this function, then this function. I'm going to pass the result of that into this function. And that's going to give me my final answer. That's a functional language. Languages that work that way. That make sense? Okay. Interestingly, and we don't have this class in our IT graduate program. We're getting ready to roll out our computer science graduate program. If you haven't noticed yet, I'm kind of our programming guy, for those of you who have had me for some other classes. So in the undergrad program, I teach our programming language theory class, which we use Scheme to write our own programming language. And actually, Davi and Diogo, you guys maybe should talk to Dr. Locklear about taking that as an elective in the grad program. I think you guys would both like that class. Class is really hard, but it's 470, CSC 470. It's programming language theory. It's not a grad class, but it's harder than any of our grad classes. So he might let you take it as an upper division elective or something. Because I think it would be good for, given your guys' background, I think it might be a good class for you. So something to look at. He might be open to that. But in any case, the reason I bring that up is we use the scheme programming language in there to write our own programming language. So we create our own programming languages in that class using a functional language. Pretty cool class. All right, so that's functional. Let's kind of leave it at that. Procedural and object-oriented. I'm going to kind of talk about these out of order because that makes it make the most sense. Let's talk about object-oriented first. Object-oriented languages allow humans to solve problems in a way similar to how they solve them in real life. And before I add any more to that, let me give some meaning to that through an example. Okay, I hold this up. We all look at this. We all know this is a cell phone. Or we might say smartphone, whatever, right? When I hold this object up, every one of us in here can identify it. Okay, it's in our brain somewhere. We know what this is. If you walk outside and you see a car in the parking lot, you know that's a car. Even though there's 1,000 different kinds of cars, they all look a little different. There's a bunch of different cell phones, they all look a little different. We understand the idea of a car, the idea of a smartphone, and we can identify it, right? We like solving problems in terms of objects. Okay? We look at this and we say, okay, that guy is identified as a smartphone. Then we can think about what can smartphones accomplish? What problems can I solve with this smartphone? Okay? So, object-oriented languages allow humans to solve problems in ways similar to how they solve them in real life because we think about things in objects. Objects are represented as only the public interfaces that make them usable. What I mean by that, we go to this cell phone here again. So this is an iPhone. Some of you are iPhone users, some of you are Android users, some of you might have something else, but I probably covered most of the class with those two. Okay? So, in any case, what are the public interfaces of this? Well, we have a screen. I have this home button here. I have the power button over here now because they copied off the Android people, right? I liked it when it was on top better, actually, personally. But whatever. My software company writes software for both of them, so I don't really have a preference. Okay. I've always been an iPhone user, but whatever. So I got my power button over here. That's a public interface. I have volume buttons over here. Public interface. I have the mute ringer switch thing here. Public interface. Got the camera here in the back. That's a public output. I can't do anything with it. The software allows me to work with that, right? But we look at this object, and what we see is a smartphone, and it's defined in terms of the parts of it that I can interact with. Now, we know there's more to this thing than what I just described. There's a whole bunch of wires and crap inside of this that we don't have to understand in order to use our smartphone, right? We believe it's there. We respect that it's there. If our phone ever breaks or something like that, if we ever have a problem, maybe you even learn a little bit about it. Sometimes, some people, you might go onto Google and learn how to replace your own screen or something like that, or you take it into one of those fix-it places, and some of the parts of these phones are actually surprisingly easy to fix. Okay? This is why some of these companies like Gazelle and stuff like that why they offer you surprisingly so much money for a broken phone. Because what you consider to be broken might only cost them $3 to fix. because they know what they're doing, right? You know, I have a buddy who's big into fixing cars. Well, he buys cheap cars from people all the time because he knows how to fix them. I don't know how to fix a car. You know, I don't fit under a car. I'm going to take it into a guy. I'm going to pay somebody to fix the car. So, you know, they're just taking advantage of their knowledge, and that's fine. Okay, but as human beings, we like to think about things like this. This is the object-oriented version of a smartphone. Okay? What we like. Now, the procedural version of the same phone. I'm going to point over to my fictitious phone over here. You walk into the room, and there's this giant pile of wires sitting on this table. And you could fish through the wires. They're all connected in just the right way. You find a screen somewhere. You find the home button somewhere in there. You find the power button somewhere in there. And as long as you put your hand behind it, you can kind of still push it. Doesn't look like a smartphone. But lo and behold, it's a smartphone. Okay? All the public interfaces are there. And all the private ones are there too. Right? That's the difference between an object-oriented language and a procedural language. Procedural languages have all the details shown. Okay? Procedural languages tend to be monolithic in nature, and both public and private details are exposed all the time. Now, there could be some gray area between procedural and object-oriented. Certainly there is in programming languages, because as we saw languages evolve from procedural to object-oriented, there was some missing links in there. Okay, we had languages that were procedural with some object-oriented features, stuff like that. We'll talk about that after the break. We're going to be talking about some comparative languages. But in any case, at the high level, really think about the difference between procedural and object-oriented with a smartphone example. Okay? A smartphone's a smartphone, but human beings like carrying around this object, utilizing the public interfaces of it to solve problems, and only having to deal with the details of it when we have to. If we had the procedural smartphone, we'd be carrying around a bucket of wires, and we have to deal with the details all the time, even though most of the time we're not going to touch them. Okay? Another example might be like if you're building a house. Somebody builds a house, they have to run all the power cables, all the wires and stuff like that through the walls, and then once all that's set up and working, then they put drywall up to cover the details, right? Because most of the time, you don't need to get to those details. But if you start having problems with an outlet or you get a water leak or something like that, now you got to break into the drywall, go and fix the problem, put new drywall up. That makes sense? So you go to the details when you have to. But once it's working, they're encapsulated inside, behind the drywall, inside the object, and we just use the object. That makes sense? That's how human beings like to solve problems in terms of objects. Okay? But that's the difference. It's not like all object-oriented languages are done in terms of procedural features. In fact, most of what we're going to do for the first several weeks of this class will be using Java, which is an object-oriented language, to solve procedural problems. Okay, we'll be writing procedural code because I won't introduce objects to you yet. Okay? All right. One last slide. There are two types of programming languages. Loosely typed and strongly typed. Okay? And I'm only going to talk about this real briefly, and we're going to actually jump back to it once we start our explanation of variables. So let me actually just throw a slide in here real quick. So when we talk about defining variables in these languages, which is our stand-in for memory, some languages require us to define what kind of value a variable is made to hold. So loosely typed languages require us to dictate what kind of, do not require us. Loosely typed languages do not require us to specify, I like that word better, what kind of value a variable is to hold. Okay? So loosely typed languages allow us to just create a variable with a name rather than a type. And we can put numbers in there 1 second, we could put characters in there another second, doesn't matter. It's a generic container. Strongly typed languages do require us to specify what kind of value a variable is to hold. So examples, Java, C++, C, C#, those guys are all strongly typed languages. Examples of loosely typed languages, PHP, JavaScript, tons of other scripting languages, Perl, okay? Now, if I'm making some connections here, we might say this. Many loosely typed languages are also interpreted languages. Many strongly typed are also compiled languages. Make sense?
But the Java and C# are also
To a point. We're talking about that after break. I'm glad you said that. Definitely not C#. I'll prove you wrong with C#. Sort of, kind of with Java. But it's actually a fun punchline. It's a good lecture if I do say so myself. All right, questions about any of that? So I'm going to leave this slide in place. I'm going to leave the variable slide there. But what I'm going to end up doing I'm going to, before we talk about variables, we're going to start off with history of languages. But this will remind me that the next thing we're going to talk about after that is variables. All right? Let's take about a 15-minute break. Get some rest, get a drink, something like that. I realize this is mind-blowing, but of course I'm a very entertaining lecturer. So it could be worse. It could be Dr. Locklear, right?